Yeah, you should start 2 minutes ago. Go ahead.
2 minutes ago.
Yeah, maybe a just formal introduction in one sentence. So,
Okay.
yeah, it's a great honor for us to have Professor Alan Sokal from University College of London and NYU, right? Who is gonna tell us about a very interesting topic in numerative and algebraic combinatorics. You see the title. So, Professor Sokal, have the floor.
Well, thanks. So you can see it's a topic a little bit at the boundary between classical analysis, the analytic theory of polynomials in the complex plane, and I guess, yeah, algebraic combinatorics, symmetric functions. So it's work in collaboration with Yusra Naqvi here at UCL, and we had some early and very important help from Richard Stanley and Lauren Williams. So you'll hear about that in a second. So, let me tell you the basic theme. The basic theme is something that I've been obsessed with in a different context, or different but related context, for, I guess, about the last 12 years. It's so upgrading a positivity property in the following sense. So let's say you have a polynomial with real coefficients in one or more indeterminates. And then there are two different kinds of positivity properties that you could consider. Well, there are probably many, but here's one of them. So one is pointwise positivity on R plus, or actually the positive octant. So that is to say, whenever all of the variables xi are non-negative, then the polynomial should take a non-negative value. Okay, so that's one positivity property you might consider. Here's another positivity property, coefficient-wise positivity. All of the coefficients are non-negative. Now that's obviously stronger, right? If you have coefficient-wise positivity and you put in non-negative values for the variables, then obviously the value of the polynomial will be non-negative. But the converse is clearly not true. For example, 1 minus x squared is non-negative. Well, non-negative not just on the positive axis, it's non-negative on the whole real line, but it's not coefficient-wise non-negative. So, the point is, lots of theorems in algebra or combinatorics or various other fields assert a pointwise positivity, and then you can ask, might it be true that they can be upgraded to coefficient-wise positivity? Sometimes the answer might just be no, but sometimes the answer might be yes, and that if it's true, it's interesting. So here's
even for some.
Oh yeah, sorry, I should say everybody, not just Doron, everybody should feel free to interrupt.
Yeah, let me just comment. Even for some of squares, it doesn't always follow, as famously Motzkin found a counterexample to Hilbert's 17th problem.
That's right. That's right. So pointwise positivity doesn't imply even that you have a sum of squares, but anyway. So I'm interested in coefficient-wise positivity. So that's and I mean, all of this was started 12 years ago because in a different context, I discovered empirically that certain polynomials that I could prove to be pointwise non-negative when x is non-negative actually turned out empirically to be coefficient-wise non-negative, and I asked myself why. And so since then, in that particular context, I've been developing methods for proving it in some tiny subclass of the cases where it's discovered empirically. So this is a different area in which the same kind of question arises. So let me try to present that. So I'm going to start with something from classical analysis, negative real-rooted polynomials, and the related Laguerre-Polya class of entire functions. So let's start with negative real-rooted polynomials. So a polynomial in one variable with real coefficients is called negative real-rooted, well, if all of its roots, by which I mean its complex roots, but all of its roots actually lie on the negative real axis, including 0 is allowed. Or the polynomial is identically 0. I mean, the point is I want to define it in a way that's closed under limits. So if the polynomial is either identically zero or has all its roots on the negative real axis, then we call it negative real rooted. And just to make things simple, let me normalize to polynomials with constant term 1. Then you can write it as a product like this, 1 plus alpha it, where the alpha i's are the negative reciprocals of the zeros. Okay, good. Now, the Laguerre-Polya class of entire functions, LP plus, are the entire functions that are limits of negative real-rooted polynomials. And there's a theorem of Laguerre that characterizes what they are. More or less, they are polynomials of infinite degree with negative roots. That is to say, instead of having this product, can you see my pointer? Yeah. Instead of having this product, a finite product, 1 plus alpha it, you have an infinite product. And of course, the sum of the alpha i's has to converge to make this product converge. The point is the alpha i's should be non-negative again. And then there's one other thing, namely you can have an e to the gamma t, which of course is kind of like a limit. I mean, you know that e to the gamma t is 1 plus gamma over nt raised to the m. So it's like lots and lots of roots go out to infinity. You have, So this is what Laguerre proved, that an entire function is a limit of negative real-rooted polynomials if and only if it's of this form. Okay. Now let me talk about total positivity. This is the concept I've been obsessed with for the last 12 years. A matrix, a finite or infinite matrix of real numbers, is called totally positive if all its minors are non-negative. And I stress all. So that means you take any set of rows and any set of columns of the same cardinality, and that subdeterminant should be non-negative. Now, I should stress this is a bizarre concept from the point of view of general linear algebra, because it's grossly basis dependent. But of course, in combinatorics, we often have a preferred basis, namely, typically matrices will be indexed by non-negative integers that count something, and you don't usually change basis there. So in enumerative combinatorics, total positivity can actually have some interesting meaning. And it has lots and lots of applications in mathematics, lots of different areas. As I said, the one that I've been obsessed with for the last 12 years is mostly this, related to the Stieltjes moment problem. But tonight this afternoon for you, I'm going to talk about two other areas, zeros of polynomials and entire functions that you've just seen, and the relation with enumerative combinatorics. So again, the basic theme again is a kind of upgrading. I want to generalize the theory of total positivity from matrices of real numbers to matrices with entries in a partially ordered commutative ring. Now, what is a partially ordered commutative ring? It's what you think it is. It's a commutative ring with a unit element, and then a subset, P, which are the so-called non-negative elements, that satisfies the things that you expect. 0 and 1 should be non-negative. A sum or product of non-negative things should be non-negative. And the only things that are both non-negative and non-positive are 0. That's what a partially ordered commutative ring is. And I stress, I do not assume that squares are non-negative. And the reason I don't is that oops, close my window. The example I have in mind as my prototypical example is a ring of polynomials with the coefficient-wise order. That is to say, polynomials with real coefficients where the polynomial is called non-negative in case all the coefficients are non-negative. So that's, and then of course, the point is you can define total positivity for matrices with entries in a partially ordered commutative ring exactly the same way that you define it for matrices with real entries. Of course, the theorems may not be the same. There are things you can do with real numbers that you can't do in a general partially ordered commutative ring. So for example, one of them is that for the real numbers, squares are always non-negative. For polynomials, you see that's not true. 1 minus x squared is not non-negative in the coefficient-wise sense. Another thing you can do for real numbers is the reciprocal of a positive real number is a positive real number. In a polynomial ring, you can't take reciprocals. So there are lots of things that may or may not carry over in the theory of total positivity to partially ordered commutative rings. It turns out some things do and some things don't. Okay, so now let me talk about total positivity of a particular kind of matrices, namely Toeplitz matrices. So given a sequence in a partially ordered commutative ring, well, in any commutative ring, I can define its Toeplitz matrix. Okay, so that's just the matrix of A sub I minus J. So it's the matrix that's constant on diagonals. And if this is a partially ordered commutative ring, I will say that the sequence is Toeplitz totally positive if its Toeplitz matrix is totally positive. That is, all of the subdeterminants of this Toeplitz matrix are non-negative. And in the case of real sequences, this is sometimes called a polar frequency sequence. And notice this implies that the sequence is log concave, because if you look at a 2 by 2 minor here, take any 2 by 2 minor, saying that that 2 by 2 minor is non-negative is saying that the sequence is log concave. But it's much stronger than log concavity because we're demanding non-negativity of all the minors, not just the 2 by 2 minors. Okay, and as I said, this definition makes sense in any partially ordered commutative ring. Okay, now over the reals, there's a nice characterization of Toeplitz total positivity, which actually looks quite a bit like what you saw about the Laguerre-Polya class of entire functions. The ordinary generating function of a Toeplitz totally positive sequence is, now it's not an entire function, it's a meromorphic function with negative real zeros and positive real poles and a possible exponential factor. So that's a theorem due to Essen, Adre, Schoenberg, and Whitney in the early 1950s. And part of the proof is fairly straightforward linear algebra. And then the last step uses Nevenlin theory of entire functions. The last step is highly non-elementary. And it would be really wonderful if some proof could be found avoiding Nevenlin theory of entire functions. But in the 70 years since then, nobody, to my knowledge, has succeeded in doing that. But anyway, we have a characterization of Toeplitz total positivity for sequences of real numbers. And special cases, the cases with no denominators, a finite sequence is Toeplitz totally positive if and only if the polynomial is negative real rooted. That is to say, there are no denominators and you have finitely many numerators. And more generally, a sequence that decays fast enough so that its generating function is an entire function will be Toeplitz totally positive if and only if that entire function belongs to the Laguerre-Polya class. It's what we saw. It's this, but sorry, with no denominators. Okay, so that's. And now let me just say one more thing about partial orders on the ring of symmetric functions. This will come up. So symmetric functions come into this game because, well, when you take a polynomial and these alpha i's are the reciprocals of the negative reciprocals of the roots, when you write the polynomial, the coefficients of the polynomial in terms of the roots, you have elementary symmetric functions coming in. So that's how symmetric functions come into the game. And so I just want to point out some partial orders on the ring of symmetric functions. So the weakest one that I would talk about is, imagine that the alphas, right? You have a symmetric function with a whole bunch of alphas, an infinite sequence of alphas being your indeterminates. If you take finitely many of them to be non-zero, and take all those to be take all of those to be non-negative, and demand that the that the function value be non-negative, that's the weakest of the sequences. Of the notions of positivity that I'll consider. But then there are stronger ones, like non-negative with respect to the monomial basis. That just means coefficient-wise non-negative. But then there are stronger ones, like Shor non-negative or E or H non-negative. And so I'll be interested in these three: pointwise non-negativity, M non-negativity, and Shor non-negativity. And so again, the basic theme is, if we have a theorem that asserts pointwise non-negativity, can we do upgradings? Might it be M non-negative, or maybe even Shor non-negative? So let me show you a simple example where the answer is yes. Just consider again this polynomial with negative real roots. So the coefficients are elementary symmetric functions. And if the alphas are non-negative, then the polynomial is negative real rooted. And using the easy half of the Asynedray-Schoenberg-Whitney theorem, it follows that the sequence of elementary symmetric functions is Toeplitz totally positive. But much more is true, because so that's a pointwise positivity result. But can it be upgraded? And the answer is yes, because the Jacobi-Trudi formula in the theory of symmetric functions tells you that the minors of the Toeplitz matrix are skew-Shor functions, and the skew-Shor functions are non-negative linear combinations of Shor functions. So we've just done a double upgrading from pointwise non-negativity to M non-negativity to Shor non-negativity. So that's the kind of upgrading that I'm going to be looking for. So now let me remind you some classical theorems from the analytic theory of polynomials. So most of these theorems were proven some in the period between about 1890 and 1920 by mostly French and German and Japanese mathematicians. So there are a whole bunch of names associated with it, and there's some really nice books nowadays on it. And the point is, the class of negative real-rooted polynomials, or entire functions in Laguerre-Polya class, is closed under several types of bilinear composition. So start with two such things. And, well, one of them is the ordinary product. Well, that's obvious, right? If the roots of f and g are negative real, then the roots of their product are negative real. That's not very interesting. More interesting is the Hadamard product, or some people call it the freshman product. This is how freshmen would like to multiply polynomials, right? You just multiply the coefficients. So this is a little surprising, that the Hadamard product of negative real-rooted polynomials is negative real-rooted. It's also true for the factorial Hadamard product, so putting in n factorial, it's still true. It's true for differential composition, do f of d dt on g of t. And it's also true for Laguerre composition, do f of t d dt on g of t. And notice t d dt on t to the n brings down a factor n. So f of t d dt brings down a factor f of n. So if you take a negative real-rooted polynomial and multiply it, do Hadamard product with the sequence, which is the values of a negative real-rooted polynomial at the positive integers, that's f of n, then it's still negative real-rooted. So you have these different kinds of composition, all of which preserve negative real-rootedness. And then we can ask, can these classical theorems be upgraded from pointwise Toeplitz total positivity to monomial or even Shor positivity? And so I've done a lot of tests mostly using Per Alexanderson's Mathematica package for symmetric functions. And the answer is almost always no, except for the one that I showed you, the Jacobi-Trudi formula. the answer is almost always no for sure, but empirically yes for monomial. So let me give you an example. So consider Hadamard product and factorial Hadamard product. So take elementary symmetric functions of an infinite set of variables x, and also elementary symmetric functions of an infinite number of variables y. You can think of those as the coefficients of two negative real-rooted polynomials, f and g, and form the Hadamard product of the sequences. That's like forming the Hadamard product of the two polynomials. And so the classical theorems say that if you take the Teplitz minors of that sequence, they will be non-negative whenever the x and y's are non-negative real numbers. But empirically, it seems that the Teplitz minors are actually monomial positive in the x and y's. You write it in the monomial basis for the symmetric functions in x and y, and you have non-negative coefficients. And the same seems to be true also for the factorial Hadamard product. And the same seems to be true for more factors. You have three factors, then you can let the power of n factorial be 0, 1, or 2. And in general, if you have k factors, you can let the power of factorial be any integer from 0 to k minus 1. So that's my first set of conjectures. Now let me give you a conjecture for Laguerre composition. So again, take En of x, those are the coefficients of a negative real-rooted polynomial, and then multiply it by f of n, where f is itself a negative real-rooted polynomial. So multiply it by something like ai plus bin, a bunch of those. And again, the claim is the Teplitz minors of that sequence are monomial positive in x, and in fact also coefficient-wise in the a's and b's. So it's coefficient-wise in both x and in a and b. So that's a conjecture.
Are there still conjectures? They're going to prove them later.
These are all conjectures. None of them are proven. Although I have heard by email that there are some Koreans who may have proven some of the conjectures for Hadamard product on the previous slide.
What about the 2 by 2 minors? For this is easy?
The 2 by 2 minors. The 2 by 2 minors are too easy because the Hadamard product of two totally positive matrices. I'm sorry, you have two matrices that are totally positive of order 2. That is, the 2 by 2 minors are non-negative. If you have two such matrices and take their Hadamard product, then that is also totally positive of order 2. That's just a very simple identity of relating AD minus BC and A prime D prime minus B prime C prime. Yeah. So for 2 by 2 minors, it's trivial. That works.
So how about 3 by 3?
3 by 3, I know nothing.
But already it's still open for 3 by 3. Wow.
I think so. Yeah. So let's see. So, and here's a variant of that conjecture. Instead of product ai plus bin, just put some real numbers cn, which have the property that cn over n factorial is an entire function in the class LP plus. Then cn is a product of a plus bn is a special case of that. It's more general, so this variant conjecture is more general, but on the other hand, it's no longer asserted coefficient-wise in A and B because there are no coefficients to talk about. So anyway, so you have both of those conjectures. Neither one is proven. Oh, and I should say, it's interesting, these conjectures. I mean, this is something I typically do. I make lots and lots of conjectures, and then I prove how I can show how some of my conjectures imply others of my conjectures, even though I can prove none of them. So the preceding conjecture on the factorial Hadamard product implies this variant conjecture because Cn over n factorial can be approximated by elementary symmetric functions. Because if this thing is in Laguerre-Polya class, it can be approximated by negative real-rooted polynomials, and then the coefficients can be approximated by elementary symmetric functions. So these conjectures are somewhat related to each other. Okay, now here's where it gets really interesting. So I gave a talk about this, I guess it was about 2 years ago at Harvard, and Richard Stanley was in the audience, and he immediately suggested the following idea for proving these conjectures, which I think is a great idea. We still haven't used it to prove the conjectures, but it's a great idea. He points out the Toeplitz minor, well, I pointed out earlier, but he reminded me, right? The Toeplitz minors of the ENs are positive linear combinations of Schur functions. So for any sequence C of which could be numbers or indeterminates or whatever, consider the homomorphism of the ring of symmetric functions defined by phi of En is Cn En. Right? The point is the ENs are generators of the ring of symmetric functions. They're independent, so you can define a homomorphism by making phi of En be anything you like. And so I'm going to let it be Cn En for n greater than or equal to 1. But notice, if I set C0 equals 1, then this holds also for n equals 0. So if you do that, then the Toeplitz minors of Cn En are just the images of Schur functions under this homomorphism. And so then the question is, are the phi C images of Schur functions themselves non-negative in, well, I'm interested in the monomial basis. And of course, that won't be true for arbitrary CNs, but one hopes that it will be true for the CNs of the kind that I want, 1 plus BIN. Notice I put 1 plus BIN because I said I want C0 equal to 1. So if I set if I want Cn to be a product of 1 plus BINs, and then what I hope is that the images of Schur functions under this homomorphism will be monomial non-negative. So let me make that more precise, because what we're actually defining is a polynomial generalization of the Kostka numbers. So recall that if lambda is a partition of n, so I have a Schur function S lambda, then I can write that as a linear combination of monomial symmetric functions, and the coefficients k lambda mu are called the Kostka numbers, and they are non-negative integers that have a combinatorial interpretation, namely it's the number of semi-standard Young tableau of shape lambda and content mu. And remember that in particular, they will be non-zero only when mu is lower than lambda in the dominance order for partitions, and also the diagonal coefficients of this matrix are 1. Okay, so for any sequence of C's, what I'm going to do is, instead of looking at S and S lambda and expanding it in monomial symmetric functions, I will look at the image of S lambda under my homomorphism, or under Richard Stanley's homomorphism, and I will call those the generalized Kostka numbers for sequence C. And I want to know, what can we say about them? In particular, what can we say about them when CNs are a product of 1 plus BNs? And what I conjecture is that these generalized Kostka numbers are polynomials with non-negative coefficients in the B's. If this were true, then it would prove all of the previous conjectures. That's Richard Stanley's idea, right? That all of the previous conjectures, if you just have the E's, the minors are Schur functions, and so if we could prove this conjecture, it would prove the preceding conjecture. Well, I have to actually, it would certainly prove the conjecture about the Laguerre composition. I think it would also prove the the ones about Hadamard product, but I actually would have to think about that. But anyway, this is the big conjecture that we're aiming to prove, that these generalized Costco numbers are polynomials with non-negative coefficients in the BIs. And so I would just say that even irrespective of this application, this strikes me as these generalized Costco numbers strike me as a very natural polynomial generalization of the Costco numbers, much simpler than the QT generalizations that other people have studied. So I think they're an interesting thing to study in algebraic combinatorics.
Do you believe there's a commental interpretation to the generalized Costco numbers, like putting some natural weights on the?
That's what I'm hoping. That's what I'm hoping, and I'll show you my incomplete conjectures about that. I mean, in fact, nothing's proven, but I'll show you a partial conjecture. So again, it's just a few remarks. Again, it's non-zero only when mu is below lambda in the dominance order. And Yusra, one of the first things she proved was that the diagonal elements are just the products of C lambda prime. That is the transposed partition. You evaluate the C's on the transposed partition. That's what the diagonal elements are. But what about the off-diagonal elements? Well, for example, we did some experiments and we have a conjecture for the case of partitions where all of the rows have either size 2 or size 1. So we have various conjectures, but let's look at this special case, and let's look at the case where there's one factor. So Cn is just 1 plus Bn. So now we have a polynomial in one variable B, which I conjecture is polynomial with non-negative coefficients. And empirically, we know some things about the degree. But here's the interesting thing. And again, this is empirical. I'm not even able to prove this, but I believe this at least is true. When lambda is just one row, then I believe that this thing is a sum over what I call marked semi-standard Young tableau. So what do I mean by that? First, there is a unique semi-standard Young tableau of just n cells in a row and content mu. So there's a unique one. And then I just choose an arbitrary subset of the cells and mark them, okay? And I'm going to sum over all choices of that subset. So I choose a subset S of cells called the marked. I form the subword consisting of those cells. Let L of S be its length, and let weight of S be the number of distinct permutations of those marked cells. So for example, if the marked cells are 1, 1, 1, then you permute, there's only one way to permute them, so then the weight is 1. If the marked cells are 1, 1, 2, then there are 3 permutations, and so on. And my conjecture is that this generalized Costco number for this special case is B to the number of marked cells with a coefficient which is the number of distinct permutations. And I've checked that up to n equals 11. So I suspect that it's true. I mean, basically, I just looked at the data and guessed this. And so it would be interesting to prove that conjecture. I don't know how to prove that conjecture. But of course, the next thing, after getting this conjecture, I said, okay, what if the partition is not just a single row? So here's my attempted generalization. For each so now, of course, so again, you look at semi-standard Young tableau of shape lambda and content mu, but now there's not a unique one. There may be many. For each contributing one, I say mark 0 or 1 cells in each column. Now, why did I say 0 or 1 cell? It's because of this fact about the diagonal elements. product of C lambda prime. If C is 1 plus Bn, that's product of 1 plus B lambda I prime. And that's screaming at you. You have a column of lambda I prime elements. You either mark nothing with weight 1, or you mark one of those cells with weight B. So that's why I said that. For each contributing semi-standard Young tableau, mark 0 or 1 cells in each column. In each row, look at the subword of marked cells. So now I'm going to just imitate what I found empirically for a single row. In each row, let SI be the subword of marked cells. Let the weights be as before, and take the product of those weights, product over all the columns, and then some over marking, some over semi-standard Young tableau. Well, this conjecture is right in a lot. It gets the diagonal elements right for the reason I just said. And it gets many other cases right, but it also gets many wrong. And already with lambda equals 3, 1 and mu equals 2, 2, it gets it wrong. Gets it wrong, just two coefficients are off by 1. So it gets it a little bit wrong. And so then I thought, or Yusra and I thought, okay, maybe we have to put some extra constraints on what you're allowed to mark. But it's turned out to be more complicated because although in the first cases we saw that this conjecture was too high, and then we thought that, okay, we need to put more constraints, it turned out that for some bigger cases, it turns out to be too low. So it's not clear. I mean, this looks like, something like this might be on the right track, but it's certainly not the right thing yet. It looks like it's the right thing for when lambda is 1 row, but otherwise we don't know.
Maybe some inclusion exclusion with alternating things.
Maybe, who knows? So I'd be happy to share the data with or share the Mathematica programs with anyone. I mean, so far we're doing exactly what this seminar is about: experimental mathematics. We haven't proven much of anything.
Yeah, it's perfect.
We're trying to guess what we should try to prove.
It's much more interesting than having proved things.
Right. Well, okay. We may be close to proving something, but unfortunately not proving what we need. So let's go back to the case of general C, because we thought that maybe the point is we should try to understand the case of general C. Well, we think we can actually. We think that the generalized Kostka number has this form. It's a sum over all nus that lie in the dominance order interval between mu and lambda. Then product of 3 factors. A product depending on lambda and nu. There's this product C nu prime that we were seeing before. And then a product G depending only on nu and mu. Where the F's are integers, but unfortunately have some signs, and the G's are non-negative integers. And we have ideas. We're close to figuring out what they are. I mean, we're still working out the details, but we think we're going to have combinatorial interpretations for F and G. But the problem is that G's are non-negative. The F's have some signs. And of course they should, because the kind of positivities that we expect don't hold for arbitrary C's. They hold for C's that are of the nice form, like 1 plus Bn, or a product of 1 plus Bn. So somehow we're going to have to use what the F's are and what the G's are, and get the positive terms to beat the negative terms when the C's are of a certain form. And that we really don't know how to do at this point. But anyway, that's the goal, to first understand these generalized Kostka numbers for general C, which we think we're close to doing, but then specialize to the CNs of the form we want to try to prove the positivity conjecture. And that that we're not sure how to do. So that's it. That's the last slide, and please feel free to ask more questions.
Thank the speaker.
Yeah, that was fascinating. Lots of good conjectures. Yeah, so it's really nice, this generalized Koska numbers, I get polynomials that you put in.
Yeah, I think even irrespective of the connection with analytic theory of polynomials, I think they're interesting things to study. As I said, people have studied these QT generalizations of the Koska numbers. These are much simpler, right? I mean, it's not a Q-like variable. It's a kind of the B's are kind of ordinary variables, and you could have one of them or many of them. And just trying to understand combinatorially, even just with one variable B, what is K lambda mu of B? So ideally, what we would like to do is have a combinatorial interpretation of K lambda mu of B, in which it's obvious that all the coefficients are non-negative. That's kind of the goal.
Do you have a conjecture for two equal rows?
No. We haven't looked at that particular case. We could. We can look, and another one that we've been looking at is n minus 1 and 1. So that would be useful to look at special cases to see whether there's some generalization of this one row conjecture that might be the right answer.
Or even the one row conjecture is still open?
Yeah, the one row conjecture is still open.
It seems that it should not be too difficult with only one row.
Yeah, that's what I would hope. Yeah. I mean, maybe there's some simple thing. I mean, as I said, I know very little about algebraic combinatorics. I mean, that's why I'm working with Yusra, who knows a lot more than I do. So yeah, maybe somebody who knows their symmetric functions well will find some easy way to prove this one row conjecture. Already that would be interesting.
So, hi, can I ask a question?
Sure, absolutely.
Okay. Could I see again the Stanley map?
Yeah, let's go back. Yeah. So it's just you map En to Cnen. That's all.
Right. So so there's another way to think about this, I think. So if you look at the generating series for the E's,
yeah,
right? Okay, so this generating series has summation of T to the N, E to the N. Right? And we know how that factors. And so I think you're applying a homomorphism there where you're sending T to the N to Cn. I mean, you could replace it by the power sum. No, let's see what's a good what's dual to En, and Doron, what's dual to En and with respect to the McDonald?
You have the.
Is it H?
Yeah, I have ENH. And
so if I take the sum,
dual, it's ENH.
E and H are duals, right?
Yeah.
Okay. So I could take summation but that H is not much of an improvement over E. Because what I'm saying is that maybe it's some two sets of variables and you're doing a specialization. You're not kind of changing the e's, but rather you're specializing the second set of variables.
Second set of variables.
Say it again?
You say seconds, you mean something.
Yeah. I mean, there's like this. I mean, if you look at McDonald's book.
You mean like I was doing here, where you have a set of variables x and another set of variables y.
Yeah. That's okay. No, but I don't know what is the summation en x en y, whether that's a good thing. But there is this there's the inner product, which is like something product of 1 over 1 minus xi yj, and it has several expansions. It is sort of in the first few chapters of McDonald's book.
Yeah.
And so you can have a series in which you have en showing up. I guess en shows up in the one variable case. That's even earlier. Okay.
No, I don't think there's going to be any simple formula for the generating function en of x, en of y, t to the n.
But it is, right? I mean, it's just the product of 1 plus txi.
No, but once you make this Hadamard product, if you have
No, I'm not talking about. I was talking about the specialization Cn goes. I mean, you were sending t to you were sending somehow t to the n, which is an exponential thing, to a linear thing in n. Let's just take 1b.
Okay, so you want to replace. You want Cn is 1 plus bn.
Right. But instead of that, I just have the series summation t to the n en. And I know how to sum this series, just the product of 1 plus t xi, right? And now, instead of t to the n, you think of that as 1 plus bn, so it's some linear function.
Right. So that's equivalent to applying the operator 1 plus bt ddt.
Yeah, something like this.
And that's exactly Laguerre composition. I mean, that's going back to.
That's how you go.
I mean, that's
okay. Sorry,
that's where this came from, right? The Laguerre composition. Where was it? Here, if f of n is 1 plus bn, so t is 1 plus bt. That is a negative real-rooted polynomial. That's the simplest case.
Yeah,
and you're doing Laguerre composition. So that's where.
Okay, that's how. Okay, fine. All right.
But
okay. Okay, sorry. Yeah. If I have some more thoughts, I'll let you and Yusra.
No, absolutely. It's conceivable that that some of these things are easy if you look at it the right way, right? I mean, I guess you all know the joke about the math professor who says that such and such is trivial, and a student raises his hand and says, I don't see it, could you please explain it? And he thinks a little more and walks up and down the corridor and walks out to the campus quad and walks all the way around, comes back a half hour later and says, yes, it is trivial.
Let's talk about something else.
and of course, it could be, right? It could be that there's some very simple argument that we're overlooking. So that's one reason why I like talking about it before we finish doing the work. Maybe somebody will beat us to it and find some way that we're not thinking about and just prove these conjectures, and I'll be happy.
Alan?
Yeah, hi. Go ahead.
I have just a comment or maybe a suggestion. So the Koska number has there are various interpretations, but there's one which is the following. So whenever I have a partition, I have what's called I think it's a row canonical tableau associated to it. So there's some special standard Young tableau of that shape.
Oh.
And then what you can do is for all of the partitions, you can take their row canonical tableau and you can put a kind of weak Brouhah order on these row canonical tableaux. You get this weak Brouhah order by doing Robinson-Shenstedt. And if I remember correctly, and I can give you a reference for this.
Oh, absolutely.
But the Kuska number itself is measuring the interval between it's basically measuring the interval between the row canonical tableau associated to mu and the row column canonical tableau associated to lambda, something like this.
Oh.
Okay. So then what it would be interesting to do with, say, your easiest case with B, right, with just one different parameter, is to somehow take the Hasse diagram of this weak order and then maybe introduce weights onto it in such a way that you're counting, maybe you can see it by somehow introducing weights onto the
I mean, you would maybe mark some. Maybe the point is some of the
elements get
some of the elements in the interval will get marked a little bit the way
based on their rank. It's a ranked. This Hasse order, so the weak order is somehow ranked. So maybe like somehow this B variable would sort of see the rank. I don't know, but like that would one possible thing to explore. And
that's really interesting.
So the name of the person who made this observation about this interval and counting the interval, I think his name is Janvier Nozichap. He's a student. He was a student of Florent Hiver in Paris.
Well, it'd be great if you could email me a reference where I can start looking at that.
Yeah,
that would be great.
I think the idea is you want to basically take the right combinatorial interpretation of Kuska and then somehow deform it.
Absolutely. And so I wasn't aware of that interpretation. I mean, I was taking the standard one and trying to deform it with these markings, and that seems to be the right thing to do for one row. And maybe there's a variant on that for more general partitions lambda, but I don't know what it is. So it's certainly worth trying this other approach. So yeah, if you get a chance to dig up the reference and email that to me, I'd be very, very thankful.
Yeah, sure.
In this conjecture right here, if k equals L, then it's probably easy, right? It just.
I'm sorry, say this again. I'm sorry. The one that's here. If k equals L, that's just the diagonal element, which we know what it is.
Right. So can you say anything about when k minus L is 1? That's the next.
I can't remember actually, because this was a conjecture we had a long time ago, and I'm not sure whether we now know how to prove this conjecture or not. This was one of the first ones we discovered empirically.
Beautiful. I think it's probably tractable for this particular special case.
Yeah, as I say, I think we're not far from understanding the KC lambda mu in general. I mean, that is giving a combinatorial interpretation of those F and G things, and then probably we can use that to compute simple special cases. But using it to prove the positivity conjecture when Cn is 1 plus Bn, that may be more difficult. We don't know.
Nice.
So that's why I'm interested in Jean's suggestion that we should try a different interpretation of Kuska numbers.
Thanks.
And another quick question that maybe not very interesting, but would it be meaningful to look at Henkel matrices instead of Choplitz matrices?
Well, Hankel matrices is my main obsession for the last 12 years has been questions of total positivity with having to do with Hankel matrices. So that's, I think they are two totally different stories, right? Total positivity of Toeplitz matrices, well, you saw it's related over the real numbers. It's the Asenadre-Schoenberg-Whitney theorem. Where was that? That's it? No? No? There. Right. So over the real numbers, total positivity of a Toeplitz matrix says that the generating function has this particular form. For Hankel matrices, it's completely different. A sequence of real numbers is Hankel totally positive if and only if it's a Stieltjes moment sequence. That is to say, moments of a positive measure on the positive real axis. So so in both cases, they relate to an interesting branch of analysis, but two different branches of analysis. And so, as I said, most of my obsession for the last 12 years has been upgradings of that. You have some polynomials which usually have some combinatorial meaning, and I know for a fact that when X is non-negative, they form a Stieltjes moment sequence. And then I want to know, are they actually coefficient-wise Hankel totally positive? And the answer is, well, in many, many cases, the answer appears to be yes. And in some small fraction of those cases, I've developed methods for proving it. But that's a totally different corner. I mean, they both have to do with a kind of intersection between a certain kind of classical analysis with enumerative combinatorics, but they're two different corners of classical analysis intersecting, I think, two different corners of enumerative combinatorics.
Right. So here you just have this nice theorem.
Right. But as I said, it's not, I mean, I was led to think about this because I was thinking about this general issue of upgrading from pointwise to coefficient-wise. That's kind of the general theme, which you can apply anytime when you have things that are polynomials and you have some non-negativity result, and you ask, can the pointwise non-negativity be generalized to coefficient-wise?
Got it. Okay. Guess it's a good time to stop unless there are other questions. And yeah, thanks again for...
Okay, thank you for having me, and I hope some of you will prove these conjectures.
And Alan, please email me the slides if you wish.
Yeah, I will email you the slides, yeah.
Thank you. Okay.
Thanks. Bye, everyone.
Thank you.
Okay, good night.
Thank you.
Good afternoon for you. Good night for me. I'm going to bed.
Good night.